Hi everyone, I'm Brendan Avent, a PhD student at the University of Southern California. I'm going to talk today about the power of the hybrid model of differential privacy for mean estimation. This is joint work with Yetart Dubey and my advisor, Alexandra Korolova. The problem of mean estimation is one of the most fundamental problems in statistical literature. Not only is it useful in and of itself, but it's also often a key subcomponent in more complex statistical tasks. So in this talk, we're going to start by defining precisely what the mean estimation problem is and what it means to solve it with differential privacy. In differential privacy, though, there are various trust models that can dictate how a solution can be computed, in turn affecting the solution's utility. We'll describe the two classic trust models in differential privacy and discuss how they each affect utility. Then we'll describe the hybrid trust model of differential privacy, which combines these classic trust models. Ideally, solutions in this hybrid model can outperform solutions in the classic models. This would be great since it wouldn't just improve the utility of mean estimates, but it would improve utility for any of those complex tasks that use mean estimation as a subcomponent. Once we've defined these models, we'll go on to developing a mean estimator in the hybrid model, which, under certain assumptions, always outperforms analogous mean estimators in the classic trust models. So with that, let's dive right into defining the basic mean estimation problem. Here, there's some distribution D that has unknown mean mu, some variance sigma squared, and support on the subset of the interval 0 to m. The goal is to take n samples from the distribution and use them to accurately estimate its mean. Framed in a user-centric perspective, we assume there are n users, each holding a single sample drawn from this distribution, and we want to collect their data to estimate the mean. Requiring the constraint of differential privacy simply adds this conceptual privacy barrier that all the user's data must pass through in order to generate the mean estimate. Now, the way that the privacy barrier functions strongly depends on the underlying trust model used. However, what it means for a mechanism to satisfy differential privacy, or in this case, for an estimator to satisfy differential privacy, remains the same across all trust models. I won't dwell much on precisely what the definition of differential privacy is, but to briefly summarize it, we say that a mechanism satisfies differential privacy if, for all pairs of inputs that differ in only one user's data, the mechanism's corresponding pair of output distributions are approximately the same. Now we can dig into what these trust models actually are. We'll first describe the two classic trust models, known as the trusted curator model and the local model. Then we'll describe the motivation for the hybrid model, which combines these two, and discuss the intuition for why we think the solutions in the hybrid model may be able to outperform solutions in the classic models. The first model we'll discuss is the trusted curator model. Here, users submit their unprivatized data directly to the curator. The curator then performs any computations it wants on the data, taking on the responsibility to ensure that these computations satisfy differential privacy. Due to the centralization of users' data, mechanisms designed for this model tend to have higher utility since the curator can very precisely incorporate the necessary randomness into the computations. Because of this, it's been one of the most studied trust models in differential privacy, and most differentially private mechanisms have been designed to be used within it. However, it has one major and obvious drawback. Users have to actually trust the curator with handling their unprivatized data, and also trust that the curator will perform the privatization properly. One way to address this drawback is to use the other classic trust model, the local model. This one is on the opposite end of the trust spectrum. Here, each user first privatizes their own data, denoted by the privacy barrier now directly on each user. Then they send off this privatized data to the curator. At this point, the curator can perform any computations at once on the data, since the differential privacy has already been ensured. This is great because it requires essentially no trust from the users. Unfortunately, the downside is the utility of mechanisms in the local model are known to typically be worse, sometimes significantly so, than the analogous mechanisms in the trusted curator model. Anytime a differentially private computation is going to be performed, one of these trust models needs to be chosen. To make this choice, we have to consider the trust preferences of the users whose data we'll be using. It's well known that people's attitudes towards privacy vary widely. Some users may not be comfortable with the curator having their unprivatized data and would only choose to use the local model. Others may be more comfortable with the curator handling their data, whether this is some innate trust or maybe due to incentives that are offered, such as early access to new features. Regardless, being able to overcome the utility barriers of the local model while still respecting the trust preferences of all users is what motivates the need for a hybrid trust model in differential privacy. Based on this need, the hybrid model is very simply defined as allowing a combination of the trusted curator model and the local model. That is, if there's some group of users, no matter how small, who are willing to trust the curator, they can opt into the trusted curator model. We refer to them as TCM group of users. The remaining users that don't trust the curator will use the local model, and we refer to them as the LM group of users. The intuition for why the hybrid model may be able to improve utility comes directly from the practical choice of which classic trust model to use when no hybrid model exists. Without a hybrid model, if the trusted curator model is chosen, then in order to not violate any user's trust preferences, only the small amount of data from the trusting users who opted in could be used. On the other hand, all users' data can be treated under the less trusting local model, but we know that the downside of the local model is that it has relatively poor utility. With a hybrid model, we can get the high utility benefits from the trusted curator model from a few users, and also not have to discard the data of the remaining users. So we want to be able to use this hybrid model to tackle the problem of differentially private mean estimation. In particular, we want to find a solution to this problem in the hybrid model that will provably always perform well compared to analogous solutions in the classic trust models. Additionally, we want precise mathematical utility guarantees for our solution so that we can know what kind of error to expect before actually performing the computation. Finally, since users self-partition into groups in the hybrid model based on their trust preferences, this opens the possibility of selection bias between the groups. Therefore, we want to determine what impact such bias may have on our solution's utility. To get started with this, we revisit the problem of mean estimation, now viewed through this hybrid lens. Our goal is still to estimate the mean of some distribution d from n samples. However, now we assume that a c fraction of those samples come from a distribution that is specific to the trusted curator model user's data, with its own mean and variance, and we need to guarantee differential privacy for their samples under the trusted curator model. The hybrid model is most interesting when the number of TCM users is small, so we can typically think of C as a small percentage, or even a fraction of a percent. Then, with the remaining 1 minus C fraction of samples, comes from another distribution that is specific to the local model user's data, with its own mean and variances, and we need to guarantee differential privacy for their samples under the local model. So now we're using a total of n samples to estimate the mean of this mixture distribution, D, ensuring differential privacy for both groups under their preferred trust models. To measure the utility of any private estimators we present, we benchmark them against the non-private empirical estimator, which computes the straightforward mean of all users' data. We can then define the utility of a differentially private estimator, mu tilde, against this benchmark as the mean squared error between mu tilde and the empirical estimator. We'll refer to this simply as the MSE of mu tilde, leaving the benchmark implicit. Now we can define the baseline estimators in the classic trust models that we'll use to compare any hybrid estimators against. For the trusted curator model, we define the TCM-only estimator, which uses only the TCM user's data to compute an empirical mean, then adds noise calibrated to ensure differential privacy. For the local model, we define the full LM estimator. Here, all users add the same scale of calibrated noise to their own data to ensure differential privacy. Then they report their privatized data. The full LM estimator just takes these reports and computes a simple mean on them. I should note that although the noise addition privatization mechanisms here seem simple, it's actually a fairly broad class, which includes two of the most popular differential privacy mechanisms, the Laplace and Gaussian mechanism. We derive the following error expressions for both estimators. To make these more intuitive, we can decompose the TCM-only estimator's error into three primary components: the excess sampling error, the privacy error, and the bias error. The excess sampling error stems from the fact that in this estimator, we're only using the data of the TCM users and discarding all the data of the LM users. The privacy error component is straightforward. It's the error required to ensure differential privacy. The bias error similarly stems from only using the data of the TCM users. However, this error is induced because the distributions between the two groups may be different. Looking at the full LM estimator's error expression, it's much simpler because there's no excess sampling or bias errors, since the data of all users is used. Instead, there's only the error that stems from ensuring differential privacy. From these, we can intuitively expect that the full LM estimator will perform relatively well when its privacy error is low, when the data variance is high, or when the two groups' distributions significantly differ. So recall that our goal is to design a hybrid estimator that performs competitively against, or preferably outperforms, the baseline estimators. Towards this, we define the relative improvement of a hybrid estimator over the best baseline estimator as this ratio between the better of the two baselines errors and the error of the hybrid estimator. At this point, we're almost able to define our hybrid estimator. We just need to define one more local model estimator first, which we call the LM-only estimator. It's very similar to the full LM baseline estimator, except now, instead of using the data of all the users, we only use the data of the LM users. The reason this wasn't proposed as a baseline estimator is because it has strictly higher error than the full LM estimator. However, we define this estimator because it allows us to state our hybrid estimator family very simply. It's just a convex combination of the TCM-only estimator and the LM-only estimator, weighted by this parameter W. Its error expression shows that it has all three error components, but with each now critically dependent on the choice of W. So now, choosing a good hybrid estimator from this family reduces to choosing a value of W, which minimizes this error. In practice, though, minimizing this error would require full knowledge of each term in the expression. Knowing the distributional variances sigma t and sigma l is a common assumption in statistical literature, so it may or may not be reasonable. However, knowing the distributional means is certainly not reasonable, since the whole point of this problem is to estimate them. Fortunately, in the case when the group's distributions are the same, referred to as the homogeneous case, the dependence on the means drops out of the error expression, leaving only the variance as a potential unknown. We'll start by examining this case, and assume the variance is known, in order to choose a good hybrid estimator from this family. In this homogeneous known variance setting, the error expression for the hybrid family becomes much simpler and contains only known terms, so we can optimize it directly to find a weighting that minimizes it. We call the resulting estimator that uses this weighting the known variance hybrid estimator, or KVH estimator. Now that we've derived it, the first question we can ask is whether it actually outperforms the baselines. Algebraically analyzing the induced relative improvement expression, we find that the KVH estimator does indeed strictly outperform both baseline estimators simultaneously, as long as the number of TCM users is less than this ratio between the privacy noise scales of both groups. As it turns out, this condition isn't restrictive at all, since most common differential privacy mechanisms satisfy it, namely the Laplace and Gaussian mechanisms. Therefore, we conclude that the KVH estimator uniformly outperforms the baselines. The logical next question is, by how much does this estimator outperform the baselines? Analyzing the relative improvement expression, we find that it's theoretically unbounded. However, we're more interested in its performance for practical scenarios. For example, when using the Laplace mechanism to ensure differential privacy in the high privacy regime, where epsilon is less than 1. Analyzing the relative improvement under these constraints reveals that it's upper bounded by approximately 2.3. So, although the KVH estimator is always better than the baselines and has theoretically unbounded relative improvement over them, in practical settings, there's a tight upper limit on what sort of improvements we can expect. To better understand the practical performance of the KVH estimator, we evaluate its relative improvement expression in the scenario where the Laplace mechanism is used to ensure privacy and where all users' data is drawn from the uniform distribution. In this plot, we evaluate the estimator's relative improvement plotted across a range of the total number of users n, TCM opt-in fraction c, and privacy values epsilon. The results are varied, but we see that our mathematical analyses are supported, since the improvement is always bounded between 1 and 2.3, with some values nearing both those extremes. In addition to the synthetic uniform distribution, we evaluate the KVH estimator's performance using a data set of over 250,000 salaries from employees in the University of California system, shown on the left. Since the n parameter is fixed with this data set, on the right we plot the heat map for the estimator's relative improvement only across a range of c and epsilon values. We see that in most of the space, the relative improvement is at least 1.5, and in a tight band exceeds a value of 2. From these results, we can conclude the KVH estimator is noticeably more useful than either of the baselines. Still staying in the homogeneous setting, we shift our attention to the case where the variance is unknown. Here, without additional statistical assumptions, an optimal weighting can't be chosen like we did before. Instead, we have to rely on a heuristically chosen weighting, which hopefully performs well. Recalling our hybrid family's error expression, we see that not knowing the variance means we don't know what sort of excess sampling error to expect. However, we still know the privacy error, so as a heuristic optimization, we can choose a W that only minimizes this portion of the expression. We call the resulting hybrid estimator that uses this weighting the privacy weighted hybrid estimator, or PWH estimator. We can now ask the same question of this PWH estimator as we did before with the KVH estimator. Does it outperform both baselines? Our analysis was able to show that there are indeed some parameter regimes where the PWH estimator outperforms both simultaneously, and we were able to precisely determine what those regimes are. But, unsurprisingly, since it's based on a heuristic, it doesn't always outperform both simultaneously. The question then becomes, when the PWH estimator is not outperforming both baselines, is it at least outperforming one? To formalize this, we define another variant of the relative improvement, represented by this lowercase r, which now compares the hybrid estimator's error to the worst of the two baselines. For a hybrid estimator to always be outperforming at least one of the baselines, we need this weaker measure of relative improvement to always be greater than 1. Such a weak condition seems like it should hold for any hybrid estimator, but we found that even within our defined family of hybrid estimators, there are many weighting choices that can make this hybrid estimator worse than both baselines simultaneously. Fortunately, though, for the PWH estimator, we were able to confirm that this improvement is indeed always greater than 1. To understand the practical performance of the PWH estimator, we revisit our scenario where all users' data is drawn from the uniform distribution and plot the estimator's corresponding relative improvements over the best baseline, shown on the left, and worst baseline, shown on the right. From the left chart, we see that the PWH estimator often performs better than the baseline estimators, and sometimes even performs competitively with the hybrid estimator in the known variance setting. We also see that one line drops below a value of 1, indicating that one of the baselines is outperforming it. So we can then turn our attention to the chart on the right and see that even when one of the baselines is outperforming the PWH estimator, it's still performing significantly better than the other baseline. Similarly, we'll revisit the real-world salaries dataset to evaluate the performance of the PWH estimator. On the right is the heat map showing the relative improvement of this estimator over the better of the two baselines. Nearly the entire space shows a relative improvement of 1.3 or higher, approaching a factor of 2 at its peak. Because of this high performance, we can skip over exploring how it performs over the worst of the two baselines. At this point, we can move on to the heterogeneous distributions case. It turns out that here, the resulting conclusions for the known and unknown variance cases are similar, so for brevity, we'll discuss them together. Examining the error expression for our hybrid family, we see that no properties of the distributions affect the error other than their means and variances. Because of this, to better understand the effect of having differing distributions between the groups, we perform two separate analyses. The first is where the means of the distributions are the same, but their variances are different. And the second is where the means of the distributions are different, but variances are the same. Rather than getting into the details of what these analyses are, I'll give you the high-level conclusions. For the case when the variances are different, we found that our hybrid estimators perform nearly as well as when the variances are the same. One interesting finding is that the estimator's performance here is actually nearly identical to the performance in the homogeneous case, when all users' data is drawn from whatever the TCM distribution is in this heterogeneous case. For the case when the means are different, we found that our hybrid estimator's performance degrades rapidly the further apart the group's means are. I recommend seeing the paper for the exact experimental setups here, but the takeaway is that our hybrid estimators perform well in the face of changes to the distribution's variances, but the performance degrades significantly when the distribution's means begin to diverge. We've covered a lot of ground at this point, so to begin to summarize, we formalized a fairly general statistical model for mean estimation within the hybrid model of differential privacy. We designed the family of hybrid estimators for computing the joint mean of both classic trust models users. And within that family, we are able to derive exact, finite sample utility expressions in order to precisely compare against baseline estimators in either of the classic trust models. Then, from this hybrid estimator family, we derived estimators for both the known and unknown variance cases, demonstrated that they achieve good utility, and examined how selection bias in the user's self-partitioning process can affect their results. Overall, for the problem of mean estimation, this shows that even with solutions as simple as a weighted combination of the classic model's estimates, the hybrid model can achieve significant and provable practical improvements. Beyond mean estimation, the hybrid model is an interesting direction of future work within differential privacy. Several important aspects about the model have started to be explored. One aspect is its usefulness for more complex applications, which my collaborators and I experimentally began to investigate prior to this work. Another interesting aspect about the model is how interactivity between the TCM and LM groups can affect utility, which has had some fascinating results published very recently. However, all of these aspects, and others, are far from being fully answered. Moreover, other types of hybrid models have been gaining traction in the differential privacy community. One is a public-private model, where most users are guaranteed differential privacy for their data, but some users are willing to contribute their data with no privacy protections at all. Another is the shuffle model, where users locally incorporate some randomness into their data for privacy, but then everyone's data is shuffled together before it reaches the curator in order to provably boost their privacy even further. These hybrid models, possibly in combination, provide significant hope that useful solutions to many difficult problems can be found while still providing strong privacy guarantees to the users. And at this point, I'll conclude. Thanks for listening.